Have you ever just looked around and wondered what is literally everything made of? I mean, at the absolute most fundamental level. Well, welcome to this explainer. Today, we're going to embark on a really fascinating journey to demystify the microscopic building blocks that dictate the shape, the feel, and basically the function of our entire universe. It's going to be a fun one.
Okay, let's dive right into this. Here's our roadmap for today. First, the blueprint of matter. Number 2, inside the atom. Third, the ultimate cheat sheet. Fourth, patterns in the table. And finally, number 5, real-world elements. Let's get to it.
So Section 1, the blueprint of matter, categorizing our world.
All right, at the absolute most basic level, everything around us that takes up space and has mass is what we call matter. And to actually make sense of it all, matter is broadly divided by its chemical composition into 2 main branches. We've got pure substances and we've got mixtures. Now, pure substances break down even further into individual elements. Think of things like iron, and compounds, like water. On the flip side, mixtures could be homogeneous, like a perfectly dissolved glass of sugar water, or they could be heterogeneous, like a handful of sand mixed with rice. It's actually a beautifully simple way to categorize what is, honestly, a highly complex world.
Moving right along to Section 2, inside the atom, the building blocks.
Okay, so now that we've kind of mapped out matter on this macroscopic scale, let's zoom way in. An atom, well, it isn't just some solid, unbreakable sphere. It's actually a highly dynamic system made of even smaller components, which we call subatomic particles. There are 3 main players you really need to know here. First up, protons, which carry a positive electrical charge. Then we have electrons, carrying a negative charge, and finally, neutrons, which, just like the name suggests, have absolutely no charge at all. They are entirely neutral.
So how are these 3 particles actually arranged? To wrap our heads around this, let's look at the planetary model of the atom, which was first introduced by Ernest Rutherford. Basically, the protons and neutrons are packed super tightly together right in the center, forming a dense, positively charged nucleus. Meanwhile, the negatively charged electrons orbit this nucleus in specific energy levels, or shells. But to truly grasp this, we need a sense of scale, because it's kind of mind-blowing. Imagine the atom is the size of an entire football stadium. If the atom is that massive stadium, the nucleus, containing all those protons and neutrons, is a dense little area smaller than a single chickpea, sitting right at the center of the pitch. Literally, the rest of it is just empty space. Crazy, right?
So if they're all made of the same stuff, what makes one atom different from another? Well, it all comes down to one very specific number, the atomic number. And this is simply the number of protons in an atom's nucleus. For instance, let's look at sodium. Its atomic number is 11. This means every single atom of sodium in the entire universe has exactly 11 protons. It's the ultimate identifier. I mean, if an atom has 6 protons, it's carbon. If it has 11, boom, it's sodium. You can think of the atomic number as an element's unique, unchangeable fingerprint.
But obviously, an atom has mass too, right? So we know our sodium atom has 11 protons. It also happens to have 12 neutrons. If you just add those together, you get 23, and that is our mass number. Now, you might be wondering, wait, what about the electrons? Don't they weigh anything? Well, actually, they are so incredibly light that we practically ignore them for this calculation. We just add up the heavy lifters sitting in the nucleus, the protons and the neutrons, and there's your mass. Which brings us to Section 3, the ultimate cheat sheet, decoding the periodic table.
Now, with over 115 elements discovered, memorizing every single one of them would be a total nightmare. Thankfully, brilliant scientists like Dmitry Mendeleev created the modern periodic table. And honestly, it isn't just a list. It is practically the universe's ultimate cheat sheet. It arranges elements in ascending order of their atomic numbers. Now, what's really interesting about this is how the specific layout of this grid reveals incredible secrets, literally just by glancing at where an element sits.
The secret code, so to speak, lies right there in the rows and columns. The horizontal rows, we call those periods, tell you exactly how many energy shells the electrons occupy. Then you have the vertical columns, the groups, and these tell you how many electrons are hanging out in the very outermost shell. We call those valence electrons. So let's say you're looking at period 3, group II, bam! That's 3 energy shells with exactly 2 electrons on the outside. It's a literal coordinate system for atomic structure. It's so cool.
All right, Section 4, patterns in the table, predicting behavior.
Because these elements are arranged so systematically, their properties actually change in highly predictable patterns. Let's look at a truly measurable one, the first ionization energy. Simply put, this is just the minimum amount of energy required to literally rip an electron away from a gaseous atom to form a positive ion. You see, because those negatively charged electrons are strongly attracted to the positively charged protons in the nucleus, you have to apply some serious force to overcome that attraction and pull an electron away.
And this brilliantly illustrates the point. When you graph this out, the pattern is just striking. Notice those really sharp peaks? Helium, neon, argon. These are noble gases, and they have completely full outer shells. That makes them incredibly stable, so it requires a massive, massive spike in energy to tear an electron away from them. Conversely, as you move down a group vertically, the atom gets bigger. And because those outer electrons are further away from the pull of the nucleus, the ionization energy predictably drops. It's just simpler to pluck them off.
And finally, Section 5, Real-World Elements, from Abstract to Tangible.
So, we've talked a lot of theory. How do these microscopic rules dictate the physical reality that we actually touch and see every day? Well, take sodium, for example. It's a group 1 element. With just one lonely outer electron, it desperately wants to get rid of it to become stable. This makes it so violently reactive that it literally has to be stored in oil. Now contrast that with magnesium, a group 2 element. It's slightly more stable, but when you heat it up, it burns with this blindingly bright, brilliant white flame. Their invisible atomic structures directly create these dramatic real-world reactions. Sodium and magnesium are just 2 of the over 80 elements that we classify as metals. And thanks to their atomic structure, they all kind of share a very specific resume. Generally speaking, they have this shiny metallic luster. They're sonorous, meaning they give off a ringing sound when you strike them. They're mostly solid at room temperature. They're malleable and ductile, so they can be hammered into thin sheets or pulled into wires. And crucially, they're absolutely fantastic conductors of heat and electricity.
Now let's contrast those shiny, highly conductive metals with a nonmetal, like sulfur. Sitting over on the right side of the periodic table, nonmetals are basically the anti-metals. They completely lack that metallic shine. They're usually very brittle, they'll easily snap instead of bending, and they are generally just terrible conductors of heat and electricity. But I gotta say, the real magic of chemistry lies in the arrangement. Take the nonmetal carbon. Carbon can exist in entirely different physical forms, which we call allotropes, all depending on how those carbon atoms are structurally arranged. If they lock into a super rigid lattice, you get a diamond, literally one of the hardest substances on Earth, used for cutting glass and making fine jewelry. But if they arrange in these sliding sheets, you get graphite, a soft material we use in pencils or as a lubricant. And if they're just arranged randomly, you get amorphous charcoal, which is great for absorbing gases and purifying water. The exact same carbon atoms, but radically different everyday uses.
And that brings us to, honestly, the most awe-inspiring realization of all. How is it that just 3 tiny particles, protons, neutrons, and electrons, can just rearrange themselves to create absolutely everything? I mean, from explosive sodium to brittle sulfur, all the way to the silicon powering the very device you're using to watch this right now. The infinite complexity of our universe is simply a masterpiece of subatomic building blocks, all following the rules of the periodic table. So the next time you look at the world around you, ask yourself, what invisible patterns are holding it all together?